Hello again, geometry students. All right, today we are on page 457, and we're going to have a good time talking about the area and perimeter of regular polygons. Again, building on what we talked about yesterday, regular means all of the sides are the same length, all of the angles inside are the same, which also the exterior angles would be the same. So we're going to start with a new vocabulary word called the apothem. Okay. And irregular polygons, and equilateral and equiangular. Well, an apothem of a regular polygon is a perpendicular segment from a midpoint of the side of the polygon to the center. Okay, and it says to the center of the circle circumscribed about the polygon. Circumscribed, circumscribed. If we break that word down, scribed means written, and circum means around. So it's a circle that is drawn around where the center is here, and each of the vertices of our polygon is on the circle. My circle is not perfect, but this is essentially what's happening. Okay. So it's saying that the apothem goes from the midpoint of one of the polygon vertices to the center of this circle. So now what does that make each of these lengths? It goes from the center of the circle to the outside of the circle, so that makes this a radius. Okay, and so what they've done here, we have a hexagon and they've broken it into 6 triangles by drawing a radius from the center of our circumscribed circle to each of the vertices. And what that's done is it's created a whole bunch of congruent triangles. Okay, so now we are going to draw all radii from the center of the circumscribed circle that you see here to each vertex. And by the way, these first couple of examples are actually showing you why the formula for area of and perimeter of a regular polygon are what they are. So, all right, part A, we drew the radii. Part B says, what is the measure of each of the central angles formed by the radii? Well, the central angles are these right here. Okay, and so the measure of each one of these, if we put them all together, they go all the way around the circle, which is 360 degrees. So then what we would have to do to find each one is 360 divided by how many central angles are there? Well, we have 6. So each central angle is 60 degrees. Okay. And then how do we arrive at our answer? Well, we divided. Next it says classify the triangles formed by the radii by their side length and verify your answer. Well, I can tell if it has a 60-degree angle here and all of these angles are going to be congruent, then these are equilateral triangles. And that won't always be the case, but it is in this case. They are all equilateral triangles. And then it asks, how is the apothem of the hexagon related to the triangles formed by the radii? Well, remember the apothem goes from the midpoint of one side to the center. So this is our apothem. Well, how is it related to this equilateral triangle? Well, it's the height of the triangle. And that's going to be important. If you remember how we find area of a triangle, we do 1/2 base times height, so we need to know the height. This side length would be base, and the apothem is now the height of our triangle. And it says find the area of the hexagon with a side length of 4. So if this entire side length is 4 right here, then what I've done is I've created a right triangle, and I can use everything I've learned about right triangles to find the distance of this apothem. I need the apothem length so that I can do 1/2 base times height. Okay, I know now that the base is 4, actually all the way across is 4. That means that this side is 2 and this side is 2. I'm just going to look at one of these right triangles. Okay, so because I just want to find the apothem. I know since this was a 60-degree angle together, that now I've got a 30 up there, and then from this 30-degree angle, I can use trigonometry. So if I know 30-degree angle, I know opposite, and I'm looking for adjacent. So I can use the cosine of 30 equals 2 over A. I'll plug that into my calculator. Cosine 30 is 0.866. If I divide 2 divided by that answer, then I get 2.31-ish. And it doesn't tell me how to round here, so I'm just going to call it 2.31. So that's the apothem right here, 2.31. Okay, this is only one way to do this, by the way. We can also use our special right triangles in just a minute, since we do have a 30 here, and this is a 90, then this is a 60. Okay, but now we have this base of the triangle is 2. Actually, the base of this whole side is 4. So if I'm finding the area of that whole triangle here, then I would do 1/2 of the base, which is 4, times the height, which is that apothem of 2.3. Okay, and I'll plug that into my handy dandy calculator. Let's see, 0.5 times 4 times 2.3, and I get 4.6. Okay, as my area of one triangle. Well, it wants the area of the whole hexagon. Well, there's 6 of those triangles, so now I'll multiply by 6, and my total area is 27.6. Okay, now there's a faster way to do this using special right triangles. So let's go back and do this with the fact that this is a 30, 60, 90 triangle. I'm actually going to redraw it over here a little larger. Here's the 60, here's the 30, and we have the 90. I know that this side is 2. Well, in a 30, 60, 90, we know that if this is x, then the hypotenuse is 2x, and then the apothem is x rad 3, x roots of 3. Okay, so if I had a 2 here, then I know that this hypotenuse would be 4, and then this apothem, this side length, this vertical, would be 2 root of 3. And so now if I plug in my area formula, I have 1/2 of the base was 4 times 2 roots of 3. Well, 1/2 of 2 roots of 3 is just 1 root of 3. So I just have 4 roots of 3. And then again, I have 6 of those triangles. So when I multiply now, I get 24 times the square root of 3. And if you want to verify and plug in 24 times the square root of 3, and we get 41.6. Now, normally I wouldn't work every problem twice, but this is a good clue to me that I've made a mistake somewhere. So hopefully you've already caught it as you were watching over here. But when I was doing my trigonometry, let's see what happened. It had to be somewhere up in here. Cosine is not, this is the problem right here. I chose the wrong ratio. I needed opposite over adjacent, which is tangent. So I'm going to do tangent of 30 equals 2 over A. And let's see if I get the answer I got with my special right triangles. Tangent of 30 is 0.577. If I do 2 divided by that answer, oopsie, 2, I'll see, I don't even know if it'll let me do that. Go back and refer to that answer again. 2 divided by, you know what else is a shortcut? I'm going to do 2 divided by the answer I get anyway, so I'm going to go ahead and do 2 times the tangent of, or 2 divided by the tangent of 30. And so this time I get let's call it 3.5. Okay, so if I plug back in the area, 1/2